Mr. President, and all dear delegates, colleagues and friends in the geothermal sector. I'll repeat my words from the reception last night. Welcome to the warm and beating geothermal heart of this otherwise cold country. This was very poetic, I thought myself. But the volcanic nature of this country was for over 1,000 years a curse and a big threat, and people would have said it was a good country to live in if not for the volcanoes. It was first last century that we turned this threat into a blessing. And today, I think we can all say that the geothermal and the harnessing of the geothermal is the greatest blessing of this country, and it adds a lot to quality of life. I'm going to give you a short presentation of what geothermal is to the Icelanders and in a global context. This is the world primary energy consumption. 80%, more than 80% is fossil fuels. The renewables are still a very, very small part, but they are increasing very, very fast. Hydropower, of course, is renewable, the most important so far, although it is not often counted among the new popular renewables. So what is geothermal? It is basically nuclear power because it comes from the decay of nuclear elements in the mantle and the crust of the Earth. It is our own energy from Earth. The rest of the energy we use comes from the sun, being wind power, hydropower, fossil fuels, or whatever. Think of that. It is supplied by the sun on a long-term arrangement. So what is the size of the geothermal resource? We have made a simple estimate, calculated the volume of the crust of the Earth. We know the specific heat content of the rocks that are measured in the laboratory, and we need know the temperature profile of the crust. If we multiply all this together, it gives us 5 exajoules of energy stored, heat energy. Mankind uses 400 annually. So if we could put 0.1% of the heat energy stored in the crust of the Earth to effective use, it would be sufficient for mankind for the next 10,000 years. This is a context and good for you to remember. There's only one little problem, and that is how to get at these 1.0%. And this is what we've been working on now diligently for 100 years. We have come some way, but not very far. Where does the geothermal fit in? It fits best in as direct use. Space heating is absolutely great. Greenhouses, fish farming industry, and so forth. Snow melting is an important thing in this country, as we have experienced this morning. We use it also for power generation. The efficient use of geothermal heat is through direct use. It is less efficiency through power production. Power production combined with direct use, like district heating, is a very good solution. But there are many places in the world where we only can use geothermal for power production, and that's a good thing if properly done. So these are the 3 popular renewables. Wind is growing exceptionally fast, tremendously fast, and we are up to 250,000 megawatts of wind power globally today. And the increase is 30 to 40% per year for the last 10 years. Solar energy is coming on as well, quite steeply the last few years. Both of these are basically subsidized energy sources. Wind is becoming more and more economical, so it's right on the edge of being self-sufficient, sustainable. But you see the green line, this is geothermal. And this is totally unacceptable, and this is one of the reasons, or maybe the main reason, that we are gathered here today. Why is geothermal growing so slowly? It is the risk in exploration and early development. It is prohibitive cost often in test drilling and before we have proven the source. It is lack of hydrothermal resources globally where we have good access to high temperatures at shallow depth and abundance of water, groundwater, to bring the heat energy to the surface. Because water is the media that connects the heat energy in the crust with the application at the surface. And then finally, it is lack of education and training. And I also think it's the conservatism, the deep conservatism of the energy industry, but I'll come back to that later. Solutions, of course, increase research and development, education and sharing of experience. That's one thing where we could help the Icelanders, sharing of experience, opening our books. We have to clear the risk profiles, who is taking the risk in each state. Then we have, in the future, new technologies to get deeper into that 0.1%, if that is the aim. I don't know what the aim is, but if we could harness 0.1%, that would be great. This is the location of Iceland. It is on the middle of the Atlantic ridge, stretching from North Pole to the South Pole. The ridge itself is 60 million years old, relatively young when the North Atlantic and the Atlantic Ocean was created. There is a huge geothermal resource or hot plume underneath Iceland. Iceland is all volcanic, and we would not exist without the volcanic activity. We also have a stable path for low pressures crossing Iceland, giving rise to great hydropower. Hydropower is the multiple of rain or precipitation and the elevation of the land. The elevation comes from the volcanoes, so half of the hydropower comes from volcanic activity, so to speak, and all the geothermal, of course. So the vast majority of the energy we use in Iceland comes from the old man himself underground, and the rest comes from heaven. This is then a geological map of Iceland. You see the volcanic zone crossing the island, and the red dots are the central volcanoes that erupt repeatedly. A lifetime or life cycle of central volcano is 500,000 years approximately. There we have high temperatures, and the molten rocks underneath are 1100 degrees centigrade. Outside the zone, volcanic zone, we have low temperature fields with temperatures up to 150, where we take out water and use directly for house heating and space heating, district heating, greenhouses, whatever. So both the high temperature and the low temperature resources are very valuable and good resources. This is the primary energy use in Iceland from 1940. It took off during the Second World War, and over the last few years it has grown almost vertically. And first came the geothermal and the hydropower, and today we have a very, very high energy consumption per capita. 80% of that is renewable hydropower and geothermal. Geothermal mainly through space heating and direct application. 25% of the power is generated by geothermal, 75% by hydropower. Only 20% is fossil fuel, and equal share for the road traffic for ocean-going fishing fleet and ocean-going vessels, and 1/3 for the airborne traffic. The coal comes from the power-intensive industry. These are the anodes for the aluminum smelters primarily, not used for energy supply. And we have a plan to eliminate fossil fuels from the road traffic and from the ocean-going vessels. It's more difficult with the airplanes, but it will come. So this is a unique sort of portfolio or energy mix of our whole nation. Here you see the same in a different way. You see the share of each for each given year, and it was primarily coal back in 1940. Now it is hydro and geothermal. This is space heating in Iceland. Development over the last 44 years. As late as in 1970, more than 50% of all houses in the country were heated by oil, and 56% by oil and electricity combined. Now geothermal is 90% of all space heating in the country, 90%, and electricity is the rest. So fossil fuel heating has practically been eliminated. And then electricity, of course, is also renewable, hydro and geothermal. This is the geothermal usage in the country: 45% space heating, 40% power generation. Snow melting is increasing, the red part, 4% today. This is quite interesting. On a day like this, we are heating our sidewalks, we are heating our parking lots to keep them free of ice and snow in the wintertime. Then we have fish farming, swimming pools, one of the wonders here. The benefit of geothermal to the Icelanders is enormous. It is estimated 500 to 800 million US dollars per annum. And that is equal to approximately 5% of the gross domestic product of the country. And this is absolutely and totally unique, totally unique. We might introduce the term of geothermal density in national economy. I just thought of it yesterday. With that reference, we would be way ahead of any other nation. This is Reykjavík in 1933, still heated by coal primarily. And this is Reykjavík today. There's no coal heating. This is Reykjavík yesterday. Sorry. We do not build houses with chimneys any longer. And this is a blessing that we seem to have forgotten. We take it as granted. It would be interesting to take the heating away and see what happened. Here you see the development of CO2 emissions from heating in Reykjavík from 1961 to 2011. And by 1998, it had been eliminated, and there's no emission, and this is how it's going to continue. This is tremendous success. Here we see the CO2 emissions that we have omitted, and by taking up geothermal, and today we would be emitting 3 million tons of CO2 annually by heating all houses by fossil fuels in Reykjavík. Instead, it is 0. So we have saved over 100 million tons of CO2 emissions through using geothermal. So what made this possible? Policy, of course, and long-term thinking, low long-term cost, forward thinking, and the oil crisis. When I mentioned policy, it was made, the decision was made when the geothermal heating was introduced to have it compulsory for house owners to connect to the geothermal system. That was, of course, very, very important. So it was not a choice. It was very much debated during times when fossil fuels were cheap. The people wanted to go over to fossil fuels, but that was not allowed, and no one disputes this any longer. So what is the cost of heating homes in Iceland? We take 100 square meters, 3 persons home, and we take the power cost and the space heating. And we compare to our neighbors in Copenhagen, Stockholm, Oslo, and Helsinki. And the cost here is just a fraction. And we use a lot of heat energy. We keep every room at 22 degrees throughout the year, even the garage. And so this adds to the quality of life. If you put it into another context, this is the number of Big Macs. 10 Big Macs for heating a house a month for an average family in Iceland, 75 in Denmark. But this is not a good comparison. It also tells me that the Big Macs are cheaper in Copenhagen than in Iceland. Anyway, we'll go a little bit into what Reykjavík Energy is and what it stands for. This is a multi-utility. This is publicly owned by 3 municipalities. It started operations in 1909. That's the oldest route, 104 years old. Then the electricity came, hydropower. Hot water district services started 1930. So it's 83 years now, continuous service and a great success. So it's services and then fiber optic services from 1999. This is the size in geothermal terms of Reykjavík Energy. We have 423 megawatts installed power production, and then we have some between 1,000 and 1,500 megawatts of thermal capacity for house heating. This tells us that we are among, if not the largest geothermal company in the world combined, heat and power. But this also tells us, and more remarkably, that geothermal companies in the world are very, very small and few. And that has to change. What are the challenges in geothermal harnessing? It is cost, risk, surface footprint. How can we minimize that? Reservoir management, so we have it operate in a sustainable manner. Induced seismicity is a new thing in Iceland in one of our power plants, and then H2S emissions that are becoming a problem, and we are working very seriously in our power plants, and the Icelandic geothermal industry combined is working very diligently and seriously on eliminating H2 emissions. We are working in two projects called Sulfix and Carbfix. Sulfix means taking the sulfur, H2S, and fixing it into minerals in the ground. Carbfix is CO2 emissions from the power plants, fixing them in minerals in the ground as well. Deep drilling is, I'll come back to that. This is the Carbfix and Sulfix from our main power plant, the largest one, Hellisheði power plant, that you will visit this afternoon if weather gods allow. We emit 40,000 tons of CO2 from the geothermal steam. That's a low number compared to coal-fired power plants, but there's quite a bit of H2S. And what we're doing, we are separating the gases from the other gases coming out of the earth. We mix CO2 and H2S with water, and we re-inject it into the ground at 500 meters depth, where these chemical components combined with the geothermal water, and it results in minerals being precipitated and then stored in the ground forever. We have been doing years of experiments and research, and it seems to be a good way forward. And if we succeed in an industrial scale, this is a breakthrough. And after that, all our high-temperature geothermal power stations will be totally clean of H2S and CO2. So this is the basic process. We have the basaltic rocks in the ground. We pump down CO2 dissolved in water, and it forms carbonates and stays forever underground, where it came from in the beginning. Same with the H2S. It reacts with the basaltic rock and forms sulfur or pyrite minerals. A few words of deep drilling. This is East Iceland Krafla geothermal field. You see a magma chamber at 3 kilometers depth. Typically, we drill 2.5 kilometers into the ground into 250 degrees centigrade or 270 temperature. We take out the steam into the turbines. A research and development program was initiated some 15 years ago. The idea is to drill deeper, down to 5 kilometers, go into much higher temperatures, much higher pressures, and much higher energy yield from the rocks. We have drilled one well that was in 2009, 4 years ago. That deep well of 5 kilometers only got down to 2.1 kilometer, because then we drilled into the magma chamber. That was sort of an accident. Probably the first time in world history that a man-made hole has entered a magma chamber of 1100 degrees centigrade. Anyway, this was in many ways a success, and the energy coming out of that well, or power, if we connected it to a turbine, would be in the order of 40 to 50 megawatts for one well. This is the theoretics. You see the conventional dry system well, 235 centigrade, 30 bars, producing 5 megawatts. And if we go to 500 bars, 250 degrees, with the same inflow of water into the well, it will yield 10 times the power. This is very exciting, but we are not quite there yet. There are many challenges in the drilling technology under these high temperatures, and then in using the steam when it comes to the surface with a very different chemical composition from the one we're using today. This is a modern drilling rig. This is how we drill. We drill directionally into the ground in all directions to find the targets. These are the challenges in drilling technology. Bottom hole assembly at high temperature, steel casing, cementing, well logging. These are all challenges that we are working on, and I believe firmly that we will overcome, but not tomorrow though. Few pictures from in the end from our power plants. This is Hellisheiði, our flagship in our company. We have visitor centers at all our power plants, and where we educate people from the street and anyone. And this is in the minds of many visitors, foreign visitors, a strange thing. People are used to see a fence and a man and a dog at the gate, but we keep it open and we are proud of our achievements. Here's another one, combined heat and power plant. Inside Reykjavík, from the hotels, you see the low temperature wells. You see there the Hilton Hotel right in front of it. If you look out of the window, you see the wellheads giving water of 125 degrees centigrade that we pump up, mixed with cold water because it's too hot to be used, and then we pump it directly into the houses at 80, 85 degrees centigrade. Well, this is a blessing. 150 outdoor swimming pools open around the year from 7 o'clock in the morning, like in this case, in the center of Reykjavík. Greenhouse, nature bath. This is in Lake Mývatn in northern Iceland. This is the Blue Lagoon that you have heard of, and many of you have seen it. I'm not going to dwell on it. This is Krafla in northern Iceland. This is Reykjanes power plant. And this is Svartsengi, where the Blue Lagoon stems from. Conclusions. Geothermal is one of the cleanest energy sources available if it's well done, well operated, properly monitored, and done with due respect to the environment. It has saved us 100 million tons of CO2 emissions in this country. It is very sustainable if done properly. It's a tremendous economic benefit. I'm almost finished. Back to this one. Again, we see the green line, which is horizontal, flat out. This we have to change. One reason, as I mentioned earlier, is the conservative approach of the power industry. I'm going to teach you a little bit. The power industry is very, very male-dominated. If that is the root for the conservatism, I don't know. In our company, Reykjavík Energy, women are 27 to 30% of the workforce. Women in management were 19% back in 2006. They are 42% today. They were underrepresented in management, and now they are overrepresented, if you could use that word. This is a quite exciting development. And what comes out of it is this. I wonder if we could apply this to the development of geothermal. Thank you all very much.